Our last topic for this session is something called the central limit theorem. The central limit theorem is the basis for all statistical inference. And what it allows us to do is to predict the behavior of random samples drawn from a population. And it also is how we determine if experimental results are statistically significant. So the central limit theorem sounds a bit formal, but I do want to go over it just so that you have some basis for understanding how statistical inference works, because it really is the basis of all experimental statistical results. Okay, so this was what the central limit theorem says. It says that if certain conditions are met, and we're going to go over what those conditions are, that the central limit theorem assures us that the distribution of sample means will be approximately normal no matter what the shape of the population may be. Now, I know that may not sound clear right now, but I'm going to show you a simulation and a picture of what that means. So let's go ahead and take a look at that simulation. Okay, well, due to technical difficulties, our simulation that I had planned to show you now is not going to happen. It's probably for the best because it might be better, something better that I can show you in person and talk through you with you through it as I'm in it with you. So no simulation today. It was just a picture of what the central limit theorem looks like. So let's go ahead and let's move on to how to use the central limit theorem. So when you want to use the central limit, there's 3 conditions that have to be in place. You have to have a good sample. In other words, the sample had to be random and independent. Your sample size has to be large. And so usually a sample size of at least 25 is large enough. And your population has to be large. Now, that's usually not a problem because if your population wasn't large, you would be studying everyone in the population, not using a sample. So the key one here is to make sure that your sample size is large. And here's what the central limit theorem says. It says is if those 3 conditions are met, then the sampling distribution, and this is a symbol for the sample means, and what this says is that the shape is normal, the center will be the same as the population mean, and the standard deviation of the sampling distribution is going to be equal to this formula, the standard deviation, that's what the symbol is here, divided by the square root of your sample size. And I know this doesn't make too much sense yet, but it will. We're going to do several examples. And it says that the larger the sample size, the better the approximation. But here's something that's really important. If the population is normal to begin with, then the sampling distribution will always be normal, regardless of the sample size. So let's take a look at a couple of examples. The first one is mostly a picture, and the second one will have a little more computation. So let's visualize the central limit theorem. So it says the figure below shows the distribution of in-state tuition and fees for all 2-year colleges in the United States for a certain academic year. And one thing to notice is that this distribution is skewed and it's multimodal, many different humps in it. So the next pictures, the figures below show the distribution of the sample mean for samples of size 30 and samples of size 90 drawn from the skewed multimodal distribution on the previous slide. So what that means is this is a picture of all 2-year colleges, okay? And so in the first graph, what we've done is we've taken a sample of size 30. So we've taken 30 colleges from this group. So college 1, college 2, college 3, etc., 30 colleges. And what we've done is we've taken that sample and we found the average tuition, the mean tuition cost of that sample, and we graphed it. Then we took another sample of 30 colleges from this distribution. We found their tuitions, we added them up, we found the mean, and we graphed it. And we did that many times. And so here's a picture of what that distribution would look like. If we did that many times, then you can see that the distribution of the sample means has a normal shape. It doesn't resemble the original distribution, but it's quite normal. In the second graph, we did the same thing, except now, instead of 30 colleges, we took 90 colleges. So we made our sample size larger. And we did the same thing. We took 90 colleges from this group. We added their tuitions together. We divided, we got the mean, and we graphed it. And we did that over and over and over. And notice the shape of this graph, again, does not resemble the original graph, but instead, it's normal. The center of each graph is in the same place as the population mean. What's different about these two graphs here is that this one has a larger spread, or in other words, a larger standard deviation, and this one has a smaller standard deviation. It's narrower. The way these standard deviations are computed is by the standard deviation of the population divided by your sample size. So in this first case, we're taking this population standard deviation and dividing it by 30. In the second case, we're taking the population standard deviation and dividing it by 90. So you can see that this number here is a larger number than this number here. And so that's a picture of the central limit theorem. We took samples, we found the means of the samples, and we graphed them. And both of them had a normal distribution. As the sample size got larger, the spread got smaller. Okay, this one on the right is more narrow than the one on the left. Okay, so that's a picture of the central limit theorem in action. And now let's do one that requires a little more computation.